4.2 light years sounds small only because the word year hides the violence of the distance. Light, moving at 299,792,458 meters per second, needs more than 4 years to cross the gap between the Sun and the nearest neighboring star system, Alpha Centauri. A spacecraft moving as fast as Voyager 1 would need tens of thousands of years to cover the same distance. Not because our engines are poorly designed, not because we have not yet found the clever shortcut. Because the universe charges a price for distance, and that price is paid in energy, time, radiation, heat, and mass. The first trap is that human beings evolved inside a small world where speed feels negotiable. A horse is faster than walking. A car is faster than a horse. A jet is faster than a car. A rocket is faster than a jet. So the mind extends the pattern forward and assumes that a starship is just the next machine in the sequence. Build it larger, feed it more fuel, use better materials, wait long enough, and the gap will close. But interstellar space is not an ocean. It is not a desert. It is not a continent with more empty land between two cities. It is a scale change so severe that ordinary engineering intuition begins to fail. The moon is about 384,400 kilometers from Earth. Apollo astronauts crossed that distance in days. Mars can be tens of millions or hundreds of millions of kilometers away, depending on where the planets are in their orbits. A robotic mission can reach it in months. Neptune is about 4.5 billion kilometers from the Sun. That is already a number too large to feel. But 1 light year is about 9.46 trillion kilometers. Alpha Centauri is more than 40 trillion kilometers away. This is the first layer, distance. But distance alone is not what blocks the journey. If space were merely large, patience might be enough. Send a ship slowly. Let generations pass. Let the machine drift. The deeper problem is that to make the trip meaningful on human timescales, the ship must move at a significant fraction of the speed of light. And the moment that happens, the question stops being travel and becomes physics. To move faster, a spacecraft must gain kinetic energy. At low speeds, the energy is 1/2 times mass times velocity squared. This means speed is not paid for linearly. Double the speed, and the energy requirement becomes 4 times larger. 10 times the speed, and it becomes 100 times larger. Even before relativity becomes important, velocity punishes ambition. Take a modest spacecraft with a mass of 1,000 kilograms, about the mass of a small car. To push it to 1% of the speed of light, about 3 million meters per second, the classical kinetic energy is roughly 4.5 quadrillion joules. That is only 1% of light speed. At that speed, Alpha Centauri still takes more than 400 years to reach, not counting acceleration and deceleration. And that is for a small, unmanned craft, without shielding, life support, structure, fuel reserves, or the machinery needed to stop at the destination. Stopping matters. A flyby is not arrival. If a spacecraft reaches another star at enormous speed and cannot slow down, it is not visiting a star system. It is crossing it like a bullet. The same energy problem that launches the craft appears again at the end. To arrive, the ship must cancel its velocity. The ticket must be paid twice. This is where the simple version hides the important part. Rockets do not just need energy. Rockets must carry reaction mass. They move by throwing something backward. The faster they throw mass backward, the more efficient they become. But the basic constraint remains. A rocket must carry the material it uses to push itself. The rocket equation, developed from the work of Konstantin Tsiolkovsky, says that the change in velocity depends on exhaust velocity multiplied by the natural logarithm of the mass ratio. In plain language, the speed you can gain depends not just on how powerful your engine is, but on how much of your initial mass is fuel, compared with your final dry mass. The logarithm is the trap. Adding more fuel helps, but with diminishing returns. To get more velocity, you need more fuel. But more fuel makes the vehicle heavier. So you need fuel to accelerate the fuel, then more fuel to accelerate that fuel. This is not a design flaw. It is a mathematical wall. Chemical rockets are far too weak for interstellar flight. Their exhaust velocities are measured in kilometers per second, while serious interstellar travel demands thousands, tens of thousands, or hundreds of thousands of kilometers per second. Nuclear propulsion improves the situation. Fusion propulsion improves it further in principle. Antimatter would be more energy-dense than chemical or nuclear fuel. Light sails could avoid carrying fuel by being pushed from outside with lasers. Each idea reduces one part of the burden. None removes the underlying physics. A laser sail, for example, does not carry propellant. That is a real advantage. But the energy still has to come from somewhere. The beam must remain focused over enormous distances. The sail must survive intense illumination. The craft must survive dust impacts at extreme speed. And if the goal is not merely to flash past another star, there must still be a way to slow down. Moving the energy source off the vehicle does not make the energy free. It only changes where the machinery lives. Then relativity enters. At everyday speeds, adding energy mostly adds speed. But as an object approaches the speed of light, the relationship changes. Einstein's special relativity, published in 1905, makes a hard claim. No object with mass can be accelerated to the speed of light. The closer it gets, the more energy is required for each additional increase in speed. The speed of light is not just fast, it is a boundary in the structure of space-time. The relativistic energy of a moving object includes a factor called gamma. Gamma is equal to 1 divided by the square root of 1 minus velocity squared over light speed squared. At low speeds, gamma is almost 1, so classical mechanics works well. At half the speed of light, gamma is about 1.15. At 90% of light speed, gamma is about 2.29. At 99%, it is about 7.09. The number rises without limit as velocity approaches light speed. This means the last increments become brutally expensive. Going from rest to half-light speed is already extreme. Going from half-light speed to nearly light speed is not just more of the same. The universe changes the exchange rate. There is a gift inside relativity, but it is not the gift people usually want. Time dilation means that for travelers moving close to light speed, the journey can feel shorter than it appears from Earth. A ship traveling at very high velocity could, in principle, reach distant stars in less time as measured on board than as measured by people left behind. The clocks separate. The body on the ship follows its own proper time. But this does not defeat the physics. It confirms it. To make the traveler's time shrink dramatically, the ship must approach light speed. To approach light speed, the energy requirement becomes enormous. Time dilation is not a loophole. It is part of the same locked system. There is also the problem of acceleration. Human beings cannot simply be snapped to relativistic speed. A comfortable acceleration of 1 g, about 9.8 meters per second squared, would feel like standing on Earth. At that acceleration, reaching a large fraction of light speed takes time, and slowing down takes the same process in reverse. For nearby stars, acceleration and deceleration are not small details. They shape the whole journey. A ship that tries to make the trip survivable must manage not only distance, but the rate at which bodies and structures can be loaded. A body is not just cargo. It is a wet pressure system filled with delicate membranes, electrical rhythms, blood flow, and oxygen exchange. Too much acceleration turns direction into force and force into injury. A machine can be built stronger than bone, but passengers cannot be redesigned without changing the meaning of the journey. Then comes the emptiness that is not empty. Interstellar space has very low density, but low density over trillions of kilometers is not nothing. Gas atoms, dust grains, and cosmic rays fill the path. At ordinary spacecraft speeds, tiny particles are a nuisance. At relativistic speeds, they become weapons. A speck of dust striking a ship at a significant fraction of light speed carries enormous energy. The ship sees the interstellar medium rushing toward it as a high-energy beam. Hydrogen atoms become radiation. Dust becomes impact hazard. The front of the ship must become a shield, but shields add mass. Added mass demands more energy. More energy increases engineering stress. Every solution re-enters the same loop. This is why the phrase empty space is misleading. Space is not a perfect road with no friction. It is thin, cold, and wide. But at extreme speed, the thinness is enough to matter. The faster you move, the more the universe in front of you turns into a storm. There is also heat. Every engine wastes energy. Every shield absorbs energy. Every life support system produces heat. In space, heat cannot be carried away by air or dumped into an ocean. It must be radiated away as infrared light. Radiators need area. Area adds structure. Structure adds mass. Mass adds energy demand. A starship is not only a vehicle. It is a thermodynamic object trying not to cook itself in vacuum. This part is well established. Energy must be conserved. Momentum must be conserved. Heat must be rejected. Radiation damages matter. acceleration load structures. No honest explanation can remove these constraints by saying the word future. Future engineering may improve materials. It may improve fusion confinement. It may build better lasers, better superconductors, better radiation shielding, better autonomous probes. These improvements are real possibilities, but they do not erase the difference between difficult engineering and forbidden physics. There are things physics allows but makes expensive. There are things physics forbids outright. Faster than light travel, as ordinary motion through space, belongs to the second category for objects with mass. The equations of special relativity do not merely say it is hard. They say that reaching light speed would require infinite energy. Infinite is not a large number waiting for a better engine. It is the end of the calculation. Warp drives and wormholes appear in serious mathematical discussions because general relativity permits strange space-time geometries in certain equations. But mathematical permission is not physical construction. Many such ideas require forms of negative energy or exotic conditions that have never been shown to exist in usable macroscopic amounts. The physics supports theoretical questions. It does not provide a confirmed route to a starship. This is where the data stops. There is no known method to send a crewed spacecraft to another star within a human lifetime, slow it down, protect it from radiation and dust, support its passengers, and pay the full energy cost using technology that exists today. There are speculative concepts. There are serious studies. There are unmanned probe ideas that may one day reach a fraction of light speed. But a civilization-scale laser pushing a gram-scale sail is not the same thing as a human ship crossing the interstellar dark and arriving intact. The hardest part to accept is that the universe is not hostile in a dramatic way. It is not blocking the path with a wall. It is doing something quieter. It is enforcing accounting. For every kilogram, energy. For every meter per second, more energy. For every passenger, life support. For every shield, mass. For every burst of speed, radiation. For every arrival, deceleration. For every shortcut, a deeper condition that must still be paid. This changes the meaning of the stars. They are visible, but not near. Their light reaches us easily, because light has no rest mass and moves along the permitted boundary of the universe. We see stars not because they are accessible, but because photons can cross what bodies cannot. Vision makes the cosmos feel open. Matter discovers the cost. A telescope is not a small version of a spaceship. It is a different relationship with distance. Light comes to us. We do not go to it. The night sky is not a map of reachable destinations. It is a record of signals that survived the crossing. That does not make exploration meaningless. It makes it more precise. Sending instruments to the outer planets was not easy. Landing machines on Mars was not easy. Flying past Pluto was not easy. These achievements matter because they happened inside the narrow permissions physics grants to slow, patient machines moving through one star system. The solar system is already vast enough to humble any civilization. The next star is not just the next step beyond it. It is a different regime. And yet the impossibility is not absolute in every form. Information can travel. Light can travel. Radio signals can cross the gap. Robotic probes might one day be built small enough, fast enough, and durable enough to send back data after decades or centuries. Human beings may learn to study other worlds through telescopes so powerful they can read atmospheres from home. The dream may shift from arrival to measurement, but the body wants arrival. The body wants a horizon that becomes land. It wants the star to grow, the planet to resolve, the door to open. Physics does not answer that desire with cruelty. It answers with scale. 4.2 light-years is the nearest case. Not the far one, not the heroic one, the nearest. And even there, the distance is not the main fact. The main fact is what must happen to matter if it tries to cross that distance quickly. It must become fast enough to make dust dangerous, heavy enough to need impossible energy, shielded enough to become heavier, and precise enough to survive a universe that does not forgive momentum. The stars are not unreachable because they are mysterious. They are unreachable because they are real.